Welcome! In this session, we'll explore LeetCode problem number 1000, minimum cost to merge stones. This is a fascinating problem that combines elements of dynamic programming and optimization. We'll break it down step by step and discuss the most efficient approach to solve it. Let's dive in. In this problem, we are tasked with merging an array of stones into exactly one pile, but with a specific constraint: we can only merge exactly k consecutive piles in one move. Each move has a cost equal to the sum of the weights of the piles being merged. The ultimate goal is to determine the minimum cost required to merge all the stones into one pile. However, if it is impossible to merge the stones into a single pile under the given rules, we should return -1. The input consists of an array of integers, representing the weights of the stones, and an integer k, which specifies how many piles can be merged in a single move. The output is either the minimum cost to achieve the merge, or -1 if it's not feasible. Now, let's explore some examples to better understand how this problem works. Consider the first example where the input is stones equals 3, 2, 4, 1, and k equals 2. Here, we are allowed to merge exactly 2 consecutive piles in each move. In the first step, we merge the first 2 stones, 3 and 2, resulting in a new pile with a weight of 5 and a cost of 5. The array now becomes 5, 4, 1. In the second step, we merge the next 2 stones, 4 and 1, into a pile weighing 5, adding another cost of 5. The array is now 5, 5. Finally, we merge the last 2 piles, 5 and 5, into one pile weighing 10, with an additional cost of 10. The total cost of these merges is 5 plus 5 plus 10 is equal to 20. This is the minimum cost for this example. On the other hand, if we were to attempt merging the same array with k equals 3, it would be impossible to reduce the array to one pile, as merging 3 piles at a time does not satisfy the conditions. For such cases, the output would be -1. To illustrate why merging with k equals 3 might not always be possible, let's consider the same input stones equals 3, 2, 4, 1, and k equals 3. Here, we need to merge exactly 3 consecutive piles in each move. However, the array starts with just 4 piles, and after merging 3 of them, we would be left with 2 piles. At this point, it becomes impossible to merge further while adhering to the condition of merging exactly 3 piles. This is why the output in this case is -1. Next, consider another example with stones equals 3, 5, 1, 2, 6, and k equals 3. Here, it is possible to merge the stones into one pile while minimizing the total cost. For the input stones equals 3, 5, 1, 2, 6, and k equals 3, the process unfolds as follows. In the first step, we merge the 3 consecutive piles 5, 1, and 2, which have a combined weight of 8. The cost of this move is 8, and the array becomes 3, 8, 6. In the second step, we merge all 3 remaining piles, 3, 8, and 6, into one pile with a total weight of 17 and a cost of 17. The array is now reduced to 17. The total cost of these merges is 8 plus 17 is equal to 25, which is the minimum cost for this example. To summarize, the problem requires careful consideration of the order of merges to minimize cost, and certain configurations may result in an output of -1 if merging to a single pile is not feasible. The constraints and edge cases help to clarify when a solution exists and how the merges should be performed to achieve the minimum cost. To solve the problem of merging stones into exactly k piles with the minimum cost, we need to carefully consider the approaches available, especially given the problem's constraints. One straightforward idea is the brute force approach. The intuition here is simple: try every possible way to merge the stones into k piles by recursively exploring all combinations. However, this method quickly becomes computationally infeasible. With n stones, the number of combinations grows exponentially, making it impossible to solve for larger inputs within a reasonable time. While this approach is conceptually easy to understand, the trade-off is its inefficiency, as the complexity is simply too high. Now, turning to a more structured solution, we explore the dynamic programming approach. Here, the idea is to use a DP table where each state, such as DP, I, J, M, stores the minimum cost to merge stones from index I to J into M piles. By breaking the problem into smaller subproblems, we aim to solve each one recursively and then combine the results. An important observation here is that merging is only possible if the number of piles reduces in steps of k1. This means that if the condition j I plus 1 m % k1 is not satisfied, the merge is impossible, and the cost is set to infinity. Another crucial aspect of the dynamic programming approach is how we compute the cost of merging. To do this efficiently, we pre-compute prefix sums, which allow us to calculate the total weight of stones in any given range in constant time. This drastically reduces overhead during the computation process. The overall complexity of this approach is O, n cubed / k, which arises from the three nested loops iterating over indices I, j, and the number of piles m. Despite this complexity, the method is far more feasible than brute force. However, there are trade-offs. The DP structure is multidimensional, and the transition logic can be complex to implement correctly. Nonetheless, this approach is promising because it balances computational efficiency with the ability to handle the problem constraints effectively. Given these factors, the dynamic programming approach was chosen as our solution strategy. By leveraging key observations, such as pruning invalid merges using the condition j I plus 1 ek % k1 = 0, and pre-computing prefix sums for constant time cost calculations, we can focus on solving subproblems efficiently. This allowed us to iteratively minimize the cost for ranges I, j, with varying numbers of piles m, ultimately leading to the optimal solution for the entire array. The dynamic programming approach stands out as the most efficient and scalable solution for this problem. With a complexity of O, n cubed / k, it is capable of handling the constraints, such as n being up to 30, within reasonable time limits. Unlike brute force or simpler heuristic-based methods, this approach guarantees a deterministic and optimal result. Of course, there are trade-offs. Implementing the DP solution requires meticulous attention to detail because of its intricate structure, but the payoff is significant in terms of correctness and efficiency. This problem serves as a great example of balancing computational complexity with implementation effort. While brute force is infeasible and simpler alternatives lack rigor, the dynamic programming strategy ensures both accuracy and performance. Ultimately, this makes it the ideal solution for solving the minimum cost to merge stones problem effectively. In this problem, the objective is to merge an array of stones into exactly k piles while minimizing the cost. The cost of merging is defined as the sum of the weights of the stones being merged. However, the difficulty lies in the dependency between subproblems because merging stones changes the configuration, which impacts subsequent merges. To solve this, we start by validating the input. If the condition len stones k % k1 = 0 is true, it means that it's mathematically impossible to merge the stones into exactly k piles, so we return -1 immediately. For cases that pass this check, we define a dynamic programming state, dp I, j, m, where dp I, j, m represents the minimum cost to merge the subarray from index I to j into exactly m piles. To transition between states, we calculate dp I, j, m by splitting the subarray into two parts at an index p, and summing the costs of the left and right segments, such that the number of piles in the left and right parts adds up to m. Here, the transition formula becomes clearer. By iterating over all valid splits p within the range I to j, we calculate dp I, j, m as the minimum of dp I, p, x plus dp p plus 1, j, y, where x plus y equals m. Next, we define the base case. If we're merging the subarray into one pile, m equals 1, the cost is simply the sum of the weights in that subarray. We compute this sum efficiently using the prefix sum array, where prefix sum, j plus 1, prefix sum, I, gives the range sum. Additionally, when merging k piles down to 1, an extra cost is incurred, so we add the total sum of the subarray to account for this. To fill the DP table, we use a bottom-up approach, starting with shorter subarrays and gradually progressing to longer ones. For each subarray, we calculate dp I, j, m for all valid values of m, ranging from 2 to k. Ultimately, the minimum cost to merge the entire array into one pile is stored in dp 0 n1 1. To better understand the mechanics, there are a few key insights to consider. First, the condition len stones k % k1 = 0 ensures that merging into k piles is feasible, as each merge reduces the number of piles by k1. Next, pre-computing a prefix sum array allows us to retrieve the sum of any subarray in constant time, significantly optimizing range sum queries. Furthermore, by restricting the number of piles m to values between 2 and k, we eliminate unnecessary computations, reducing the complexity of the DP table. For data structures, we rely on a 3D DP table, DP, I, J, M, which stores the minimum cost for every subproblem. The size of this table is proportional to O, n squared asterisk k, where n is the number of stones. Additionally, the prefix sum array, of size n plus 1, supports efficient range sum calculations. From a complexity standpoint, filling the DP table involves iterating over all subarrays in O, n squared, considering all splits in O, n, and processing up to k pile configurations. This results in a total time complexity of O, n cubed asterisk k. The space complexity, dominated by the DP table and prefix sum array, is O, n squared times k plus n. Finally, we address some important edge cases. If the input array contains only one stone, no merges are needed, and the cost is 0. When k is larger than the number of stones, merging into k piles becomes impossible because there aren't enough stones to split. In such cases, the solution should handle this appropriately. On the other hand, if the array is already a single pile, no merging is required, and the cost remains 0. These scenarios emphasize the importance of validating edge conditions to ensure robustness and correctness in the algorithm. Here, we start by defining the merge stones function within the solution class. The first thing we do is calculate the number of stones, n, and check if it's even possible to merge all the piles into exactly k piles. This is determined by the condition n(k) k1 equals 0. If this condition is true, we return -1 immediately because it's mathematically impossible to perform the operation. Next, we create a prefix sum array, which allows us to calculate the sum of any subarray efficiently. This is done by iterating through the stones array and building the prefix array such that prefix I plus 1 contains the sum of the first I plus 1 stones. This will be handy later when we need to calculate the cost of merging ranges. Now, we define our dynamic programming table, DP. This is a 3D array where DP, I, J, T represents the minimum cost to merge the stones in the range I to J into T piles. Initially, we fill this table with infinity, as we will be looking for the minimum costs. For the base case, merging a single pile always has a cost of 0, so for any I, DP, I1 is set to 0. Finally, we begin solving for subproblems by iterating over increasing lengths of subarrays. For each length, we calculate the range from I to J and work on merging the stones in that range. At this point, we start exploring the different possibilities of merging the range into T piles, where T can vary from 2 to K. To find the minimum cost of merging a range into T piles, we iterate through possible midpoints, which divide the range into two parts. The key here is that the two parts must satisfy the merging rules. Specifically, for merging into T piles, we consider splitting the range at intervals of K1, as this ensures the merging process aligns with the problem's constraints. For each midpoint, we calculate the cost of merging the left segment into one pile and the right segment into T1 piles, then combine these costs. We take the minimum cost over all valid midpoints. Once we've calculated the cost of merging into multiple piles, we handle the special case of merging the range into a single pile. To do this, we check if it's possible to merge the range into exactly k piles. If so, the cost of merging into one pile is the cost of merging into k piles plus the sum of the entire range, which can be quickly calculated using our prefix sum array. If merging into k piles is not possible, the cost remains infinity. Finally, after processing all ranges and possible pile counts, the answer to the problem is the value stored in DP 0 and 1, 1, which represents the minimum cost to merge the entire array into one pile. This value is returned as the result. Here, we begin by defining the merge stones method, which takes an array of stones and an integer k as input. The first step is to check if it's possible to merge all piles into exactly one pile. This is determined by the condition n(k) k1 equals 0. If this condition is true, it's impossible to achieve the desired result, so we return -1. Next, we create a prefix array to store cumulative sums of the stones. This allows us to calculate the sum of any subarray efficiently, which will be useful later. After that, we define a 3D dynamic programming table dp, where dp, I, j, t represents the minimum cost to merge the stones from index I to j into t piles. To ensure we start with a clean slate, all values in this table are initialized to integer.max_value. Finally, we set up the base case. Merging a single pile costs nothing, so dp, I1 is initialized to 0 for all valid indices I. Now, we proceed to solve the subproblems for increasing lengths of subarrays. For each subarray length, we iterate over all possible starting indices I and calculate the ending index j based on the length. The goal is to determine the minimum cost for merging the stones in the range I, j into different numbers of piles. For t piles, or t ranges from 2 to k, we explore dividing the range into two parts. The division point mid is chosen such that the left part merges into one pile and the right part merges into t1 piles. If both parts are valid, we update dp, I, j, t with the minimum cost. Additionally, if merging the entire range into one pile is possible, we calculate this cost by adding the sum of the range, which is derived using the prefix array. This value is stored in dp, I, j1. By iterating over all subarray lengths and possible divisions, we systematically build solutions for larger and larger subproblems. Finally, the method returns the result stored in dp, 0, and 1, 1. This value represents the minimum cost to merge the entire array of stones into a single pile. By structuring the solution with dynamic programming, we ensure that each subproblem is solved optimally and reused efficiently, allowing us to handle the constraints of the problem systematically. In this example, we're given the array of stones 3, 2, 4, 1 and instructed to merge them into exactly one pile by merging k equals 2 piles at a time. With n equals 4, we first verify if merging is possible by checking the condition %, k1. Here, 4 to 2%, 2 to 1 equals 0, confirming that it is feasible. Next, we compute the prefix sum array to quickly calculate the sum of any subarray. Starting with prefix 0 equals 0 and iteratively adding values from the stones array, we arrive at prefix equals 0, 3, 5, 9, 10. The next step is to set up our dynamic programming table. This dp table, dp, I, j, t, will store the minimum cost to merge the subarray stones, I, j plus 1, into t piles. Initially, we set all values to infinity, except for the base case where merging a single stone into one pile costs 0, so dp, I1 equals 0. Now, we calculate the dp values in a bottom-up manner, starting with subarrays of length 2. For I equals 0, j equals 1, merging 3, 2 into one pile involves adding the cost of merging into two piles, which is initially infinity, and the sum of the subarray, 5. This gives dp, 0, 1, 1 equals inf plus 5 equals 5. Similarly, for I equals 1, j equals 2, merging 2, 4 costs 6, and for I equals 2, j equals 3, merging 4, 1 costs 5. Moving to subarrays of length 3, for I equals 0, j equals 2, merging 3, 2, 4 into two piles can be splitted mid equals 0, resulting in dp 0, 2, 2 equals dp 0, 0, 1 plus dp 1, 2, 1 equals 0 plus 6 equals 6. Adding the merge cost gives dp 0, 2, 1 equals 6 plus 9 equals 15. Similarly, for I equals 1, j equals 3, merging 2, 4, 1 with k equals 2 piles and splitting at mid equals 1, we get dp 1, 3, 2 equals 0 plus 5 equals 5. Adding the merge cost results in dp 1, 3, 1 equals 5 plus 7 equals 12. For subarrays of length 4, we consider the entire array 3, 2, 4, 1. To merge this into one pile, we first compute the cost of merging into two piles by testing possible split points. Trying mid equals 0 gives dp 0, 3, 2 equals dp 0, 0, 1 plus dp 1, 3, 1 equals 0 plus 12 equals 12. Finally, we add the cost of merging the two piles into one using the total sum of the array, which is 10. This results in dp 0, 3, 1 equals dp 0, 3, 2 plus sum 0, 4 equals 12 plus 10 equals 22. The minimum cost to merge the entire array into one pile is therefore 22. In this second example, we're given the stones array 3, 5, 1, 2, 6 and k equals 3. Here, n equals 5, and we check the condition end k percent k1. Since 5 to 3 percent 3 to 1 equals 0, merging is again possible. We compute the prefix sum to speed up range sum calculations. Starting with prefix 0 equals 0 and adding the cumulative sums from the stones array, we derive prefix equals 0, 3, 8, 9, 11, 17. As before, the DP table is initialized with all values set to infinity, except for the base case where merging a single stone into one pile costs 0, so DP I1 equals 0. Using the bottom-up DP approach, we first tackle subarrays of length 3. For I equals 0, j equals 2, merging 3, 5, 1 into one pile involves first splitting into two piles. Trying mid equals 0, we compute dp 0, 2, 2 equals dp 0, 0, 1 plus dp 1, 2, 1 equals 0 plus 6 equals 6. Adding the merge cost gives dp 0, 2, 1 equals dp 0, 2, 2 plus sum 0, 3 equals 6 plus 9 equals 15. Finally, for the full array of length 5, 3, 5, 1, 2, 6, we compute the cost of merging into three piles, testing possible splits. After calculating and adding the merge cost, the minimum cost to merge the entire array into one pile is found to be 25. To analyze the time complexity of our solution, we begin with the prefix sum calculation. This step involves iterating through the entire stones array once to generate the prefix sum array. Since we only traverse the array of size n one time, this operation has a time complexity of O(n). Next, we need to initialize our dynamic programming table, which is a 3D array with dimensions nx and xk. Since every cell in this table must be initialized, the time complexity for this step is O(n squared * k). These two steps lay the groundwork for our solution and contribute to the overall computational cost of the algorithm. The most computationally intensive part of the solution is filling the dynamic programming table. This process involves several nested loops. The outermost loop iterates over the possible lengths of subarrays, from 2 to n, resulting in n1 iterations. Within this loop, we iterate over potential starting indices I of the subarrays, which can run up to n times in total. For each subarray, we also iterate over the possible values of t, which ranges from 2 to k and contributes up to k1 iterations. Then there's the innermost loop, where we evaluate partition points mid within the subarray, stepping by k1. This step has a complexity of approximately O(n/k) in the worst case. For each combination, we perform constant time operations like addition and comparison. Multiplying all these factors together gives us a total time complexity of O(n*k*n/k), which simplifies to O(n cubed). Finally, extracting the result from the table is a simple lookup operation, taking constant time, O(1). Therefore, the overall time complexity of the solution is dominated by the DP table filling step, which is O(n cubed). Now let's examine the space complexity of the solution. The primary contributors to space usage are the prefix sum array and the dynamic programming table. The prefix sum array has a size of n+1, meaning it requires O(n) space. The DP table, on the other hand, is a 3D array with dimensions nx and xk. This means its space complexity is O(n squared * k), as it grows with both the size of the input and the parameter k. When we combine these two components, the total space complexity becomes O(n plus O(n squared * k). Since the second term dominates, we can simplify this to O(n squared * k). This memory usage is significant but necessary for efficiently solving the problem using dynamic programming. To better understand why the optimized approach is so effective, let's compare it to a brute force method. A naive approach would involve exploring all possible ways to merge the stones step by step, keeping track of the cost at each stage. This would require evaluating every possible partition of the array, leading to an exponential time complexity of O(k) to the power of n. Such an approach becomes computationally infeasible as the input size grows. In contrast, our optimized solution leverages dynamic programming to reuse results from subproblems, drastically reducing the complexity to O(n cubed). This improvement is achieved by systematically breaking down the problem and using the prefix sum array for efficient subarray sum calculations. For best, average, and worst-case scenarios, we note that the time complexity remains O, n cubed. However, the constants may vary. For instance, when k equals 2, the inner loop simplifies, resulting in fewer iterations and a smaller constant factor. On the other hand, when k is larger, while the innermost loop iterates less frequently, the larger DP table size contributes to the overall cost, keeping the time complexity at O, n cubed. Finally, let's verify the theoretical bounds for our solution. The time complexity of O, n cubed, is derived from the structure of the nested loops. The innermost loop iterates approximately O, n/k, times, and when combined with the outer loops, which iterate O, n squared, times, the total comes out to O, n cubed. Similarly, the space complexity is dominated by the size of the dynamic programming table, which has dimensions nx and xk. This results in a space complexity of O, n squared * k. Both the time and space complexities align with the constraints of the problem, confirming that the solution is efficient and feasible for the given input limits. Now, let's look at some common mistakes encountered in solving this problem. First, it's crucial to handle the k-piles merge condition properly. A common mistake is skipping the check to ensure that merging the piles into exactly k-piles is even feasible. Remember, for a valid solution, the condition n1% k1 = 0 must be satisfied. If not, the problem is unsolvable, and failing to account for this can lead to incorrect answers. Next, relying on brute force to calculate the cost of merging all possible subarrays is another pitfall. This approach has an exponential time complexity, making it completely infeasible for larger inputs. Instead, you need to employ a more efficient strategy like dynamic programming. Another frequent error occurs with prefix sums, or incorrect indices, or forgetting to pre-compute the sums can introduce off-by-one mistakes. Always ensure the range sum is calculated correctly as prefix j plus 1, prefix I. Lastly, in dynamic programming, overlooking how states depend on each other can lead to flawed solutions. For example, failing to consider the number of piles at each step or incorrectly defining transitions can undermine the approach. It's key to carefully design both the DP states and their dependencies to avoid these errors. Additionally, ignoring edge cases is another common source of mistakes. Scenarios like having only one pile, k being greater than the array length, or handling very large inputs should always be tested to ensure your solution is robust. From an interview perspective, this problem is a great opportunity to demonstrate pattern recognition. It's a classic interval dynamic programming problem, where decisions for merging depend on overlapping subproblems. Highlighting this connection and explaining how the state depends on the range of piles and the number of piles being merged is essential. This also ties into the concept of optimal substructure, where the solution can be built by combining results from smaller subproblems. Interviewers often appreciate candidates who can articulate these concepts clearly. Furthermore, be prepared to discuss trade-offs, such as the balance between space and time complexity. For example, using a 3D DP table is intuitive but may require more memory, while optimizing for space can make the implementation more complex. Finally, focus on writing clean, modular code and explaining your choices for state variables and transitions. Interviewers might also test your understanding by asking about edge cases or potential optimizations. To build a deeper understanding, it's helpful to explore related problems that share similar patterns. For instance, LeetCode 312, burst balloons, is another interval DP problem where the goal is to maximize coins by bursting balloons in an optimal sequence. It emphasizes the importance of sequencing decisions, much like merging piles in this problem. Another example is LeetCode 1007, minimum domino rotations for equal row, which focuses on minimizing operations to achieve a specific condition. While not an interval DP problem, it shares the theme of optimization under constraints. LeetCode 1547, minimum cost to cut a stick, is a closer parallel, as it also involves partitioning intervals, in this case, cutting a stick into segments with minimum cost. Finally, LeetCode 1130, minimum cost tree from leaf values, features merging or combining elements to minimize costs, with a focus on tree-based structures. By studying these problems, you can strengthen your grasp of different variations of dynamic programming and gain transferable insights for tackling similar challenges. Looking at alternative approaches, a greedy algorithm might seem appealing at first glance, where smaller piles are merged first to minimize costs. However, this approach fails for many cases because it doesn't account for the implications of future merges. Greedy methods are not optimal for this problem. Another option is using recursion with memoization in a top-down approach. This can be more intuitive to implement, especially when mapping out the transitions step by step. However, it may come with a higher memory overhead due to the recursion stack and memoization table. A bottom-up dynamic programming approach is generally the most efficient and preferred method. It avoids the recursion stack overhead and systematically builds the solution. That said, the implementation can be more complex and less intuitive for beginners. For those looking to optimize further, a careful analysis of state dependencies can sometimes reduce the 3D DP table to a 2D table, significantly saving space. However, this optimization often increases implementation complexity, as managing reduced states requires additional attention to detail. Each approach has its trade-offs, and understanding these can help you choose the best method for the problem at hand. Great job! We've successfully walked through the minimum cost to merge stones problem. Remember, mastering dynamic programming takes practice, so keep at it. If you enjoyed this session, please like, subscribe, and share. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!